Escape velocity. Better metrics for Agile teams. Let's talk about velocity, so let's get started and talk about velocity. Now, I've been doing this for quite a while. This being Agile development, Agile coaching, quite a while being about 35 years. Okay, so to be fair, 35 years in software, give or take. And I've been doing Agile since about 1999. So end of 99, I picked up the XP Explained book and kind of went from there. And I've since studied XP, Scrum, Crystal, Agile Up, several others. And velocity's been around for quite a while as a concept. When I work with teams, a lot of times I ask them some things about their velocities. I try to get an understanding of where they are. And the first question I usually ask is your velocity roughly the same from iteration to iteration? The truth is that for most teams, that's not the case. It's just not the same from iteration to iteration. Now, for you, that might be the case, and that may be another discussion for us to have at some other point as to how you got there and what that does for you. But for most teams, or for many teams, it's not the same from iteration to iteration. For those where it is, the next question I ask is there a direct correlation between velocity and deployment? What I mean by that is, are the features that you build in a given iteration, are those features released in the same iteration? And again, for a majority of teams that have made it this far through the questionnaire, the answer is no. For most teams, even if they have a stable velocity, it's the same from iteration to iteration. There is no correlation between velocity and deployment, right? But for some teams, that is the case. So then I'd ask them, using velocity alone, can you predict when a batch of functionality will be in production? So in other words, a customer asks for an entirely new module and they want it by a certain date. Using your velocity alone, can you determine if, in fact, that module will be done by that date? The common answer there is no, but for some teams, the answer is yes. And then the final question is, have you used velocity alone to accurately diagnose a team issue other than an issue with velocity? And in most cases, again, the answer is either no or it's yes. And then when we actually dig into the details, it turns out that they used something other than velocity or in addition to velocity to figure it out. They did not use velocity alone. So it's kind of led me to, over the years, to the conclusion that really velocity is useless. Right? That's not fair. Velocity is nearly useless. For most teams, it isn't stable enough to be used reliably. If it is stable, it's disconnected from actual deployment or delivery. If it's connected to deployment or delivery, it still doesn't account for any other aspects of the process, such as cycle time, lead time, when the work is requested to when it's actually done. It isn't good for large-scale predictions, and on and on and on. Velocity is nearly useless. So it really leads to the question of, why is velocity nearly useless? But I think that question in and of itself isn't very helpful. What we really want to know, let's start, I guess, with what is velocity and how do we use it? And those two combined might give us some insights. So, of course, what is velocity? Well, common definition of velocity is work units over time. You can call them story points. You can call them work units. You can call them cards. You can call them stories. You can call them JIRAs. I don't care. There's some kind of unit of work over time. You can call it a sprint. You can call it an iteration. You can call it a cycle. Again, don't care. Fundamentally, you take the amount of work that was done in a period of time, you divide it, and you get a velocity. Wait, no, that's speed. Yeah, velocity has to have a vector. Okay, so you take the amount of work that you've done in the time that it took to do it, you divide those two things, and you determine that you are headed towards happy customer. So work units over time towards delivery of value or happy customer or customer satisfaction. But now you're oriented, so now you've got an actual true velocity. Great. But that doesn't necessarily help us a whole lot. Let's dig deeper. What else is velocity? Well, I think this is important. I think that velocity is a lagging indicator. It's a measure that tells us what happened. It tells us about something that happened previously. Now, lagging indicators are common, and there's a few things that we know about all lagging indicators. One of the things that we know about all lagging indicators is that they're good for confirming long-term trends, but they're not necessarily good predictors. Now, what we're looking at here is an unemployment line. If the unemployment rate is rising, it's because the economy has been doing poorly. So what happens? The economy does poorly, and then we see unemployment rising. So unemployment is a lagging indicator of a sagging economy or a bolstering economy, right? The up and down. We can know how unemployment is trending, but we can't actually know where it's going to go next. We can forecast the trend, but it doesn't mean this can continue to trend that way. And let me show you something else to really kind of drive this concept home. So this is sales. What we've done is I've redacted out a bunch of different things. This is quarterly sales revenue for a subset of retailers in the U.S. So we look at this. From this, we cannot use the prior quarter to predict the next quarter. Right? We can see that Q1 is always less than Q2, is always less than Q3, is always less than Q4. So we can see a long-term trend. You can see that basic pattern occur year after year after year after year. But what we can't know is, based on Q3, what's going to happen specifically in Q4. And I'm going to hone in on this. Let's take a look at Q3 of 2008. Now I want you to scan your eye across and look at Q3 of 2013. 2008, 2013, Q3 is roughly, if not exactly, the same amount of money. Now, look at the Q4 for those years. 2008 is significantly lower than 2013. If Q3 were a predictor of Q4, those Q4s would be the same, would they not? The point here is that lagging indicators are good for long-term trends, but they are not good for short-term predictions. All right, what else is velocity? Well, I think it's important to recognize that velocity is a measure of a complex system. You have inputs, that is requests and features and stories, and you have outputs, and that is hopefully working software. And in between all of that, you've got different cycles and different rituals, and you have a whole bunch of different people involved. You've got product owners and product managers. You maybe have team leads and team managers. You've got scrum masters. You've got the team. Hopefully you have the customer. You probably have a customer proxy. You've got designers. You get the idea, right? Lots of folks, lots of process, and every once in a while, maybe it's every week, every 2 weeks, whatever, we take a measure of work done. That's our velocity or our throughput. So velocity is a measure of a complex system. Great. So it is a lagging indicator that is a measure of a complex system. That's interesting. Doesn't necessarily help me reason about velocity. I don't know anything more about it than I did previously, perhaps. Like, I know lagging indicators aren't good short-term predictors, and I know that complex systems are, well, complex. So I got thinking about it. What's something that's a lagging indicator for a complex system? Something that might help me reason about velocity in a different way. Well, it turns out that your body weight is a lagging indicator of a complex system. We can compare body weight to velocity, and maybe these things are comparable in some ways. So it is true that your body weight is a lagging indicator, and I think we could probably agree that your body functions are complex. There's inputs, there's processes, there's outputs, and you can take a measure every so often, and it tells you something about those inputs, those outputs, and those processes, right? So what are things that affect our body weight? Well, diet, exercise, genetics, our physical health, our mental health, the environment that we're in, the work that we do, the stress that we're under, and our social network. Our friends and family actually have an impact on our body weight. Okay, great. Let me ask you this. Does a given body weight mean that you are healthy? And let me get more specific. I tell you that my friend Pat weighs 100 kilograms or 220 pounds. And I ask you, is Pat healthy? You can't answer that question. You can't possibly know that. You don't know enough about Pat. You don't know Pat's age. You don't know Pat's vocation. You don't know Pat's gender. You don't know Pat's genetic history. You don't know enough about Pat to be able to answer that question, right? Pat might be a professional athlete, and that seems a little light for Pat. Or Pat might be a third grader. That seems a little hefty for Pat. Don't know. Same thing is true for a team. Does any given velocity mean that your product or team is healthy? And the answer to that is pretty much no. Of course, there's some lower bound. The velocity is 0, there's probably a problem. Just like if your weight were 0, there's probably a problem, right? The thing with velocity is there isn't even a norm that we can compare against. At least for humans and body weight, there's norms, and there are low ends and high ends. It's contained. Velocity, we don't know. You cannot really determine anything above 0 if that product is healthy or if that team is healthy. Let's dive into this a little bit more. going back to the weight analogy, how might someone lose weight? Let's say that you wanted to lose 5 kilos or roughly 10 pounds. What are some things that you could do? Well, you could certainly reduce calories. You could change your exercise routine. You could get more sleep. You could cut back on certain foods. All of these things are relatively reasonable. All of these things have a potential to lead you towards the goal that you have for your weight. But what if you didn't understand human bodies very well? What if your focus was very strictly on losing that weight and not on anything else? What else might you do? Well, you might consume nothing but amphetamines. You could stop drinking all liquids, including water. You could smoke crack for a while, or you could cut off a forearm. Now, those things may sound ridiculous to most of you. I hope that they do. The point here is really simple. Moving the metric in the desired direction doesn't necessarily improve the health of the overall system, and it might even hurt it. And the thing is, this is also true for velocity. If you want a team to increase or stabilize their velocity, what are some things that they might do? Well, they might limit their work in progress. They might reduce their batch size. They might reduce their dependencies. But again, if they're not thinking about the overall system, if they are myopically focused on achieving that velocity goal, that target that they have, what else might they do? Well, they might skip testing. They could cut corners on internal quality. They could work more hours per week, or they could increase all of their estimates if they want to take the really easy road. And again, the point here is the same, and it's still simple. Moving the metric in the desired direction doesn't necessarily improve the health of the overall system, and it might even hurt it. Now, this happens to us at work all of the time. With good intentions or not, bosses set goals, or they ask for improvements in indicators like this. They ask us to do a stretch target on our velocity, or they ask us if we'd, if there's any way that we could increase it a bit in order to make the deadline, right? When this happens, they're almost guaranteed to create problems. So first of all, there's this law in economics, which applies to knowledge work and other complex domains. This law is known as Goodhart's law, and it states any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. All right, it's a lot of words, it's a little academic. Let me paraphrase. When a measure becomes a target, it ceases to be a good measure. Given a target and proper incentives, people will hit the target by whatever means necessary. And this is in general, this is perverse incentives. There are a number of different ways that this happens, but fundamentally what occurs is we have the intention of a good outcome, a beneficial outcome, but because we behave in a particular way, or we've done something, we've changed the system in a particular way, we get an unintended result, which is contrary to the interest of the incentive makers. Now, it's interesting to me is how often I hear managers say things like, well, the employees gamed the system. So a manager creates an incentive structure, an incentive system, and then complains because the employees gamed it. Now, let's get this straight right now. Managers game the system by setting goals for measures. The rest is just natural consequence. If you indicate that you're going to give a reward, a financial reward, or promotional opportunities, or bonus, benefit, vacation time, whatever it is, you're going to give a reward for bugs found, you know what's going to happen? You're going to get more bugs reported. What's going to be amongst those? Bugs that are of low importance. You're going to get duplicate bugs that people are going to insist are separate because of some kind of a nuance. You're going to have more arguments about whether or not that's a missed feature or an actual bug. Is that a defect or is it a blah, blah, blah? Right? So you're going to get more reported, but it wouldn't necessarily mean that you're going to capture more bugs. Same thing. If you do a reward for code coverage, I can guarantee you're going to get an increase in code coverage, but it does not mean that you're going to get better test quality. Right? In fact, you'll probably get decreased test quality overall. And a reward for higher velocity, it's going to lead to more brittle code, lower test coverage, more bugs, all kinds of side effects. All right, so a little bit of a digression there maybe, but we talked about what is velocity. We know that it's a lagging indicator of a complex system, and we know, and we know that trailing indicator is not particularly good for short-term predictions, and we know that setting targets for those types of metrics change the meaning of the metric and can lead to adverse behavior, right? So if we know that, and it's interesting when we look at how is velocity used in our industry. There's a few different ways fundamentally that velocity is used. One is to gauge when planning our iterations, right? So we look at our prior velocity and we try to determine if we can get the same amount of work done in an iteration or a sprint, and sometimes try to determine really what that means is that we ask the team to make a commitment to hitting some target. And oftentimes we ask the team to make a commitment to stretch that target just a little bit. No worries, folks. So one standard use of velocity is to set targets for a lagging indicator of a complex system, which we know leads to adverse behaviors, right? The other thing that we use it for is to determine if we're tracking to our iteration goals or release goals. So you've seen these burn up, burn downs. They are within an iteration or a sprint. They're also across a release cycle if those are different, or they are for a set of features that you're targeting, etc. Now, this fundamentally is really just a means of forecasting, right? So the way that we are predicting our iterations and the way that we're tracking releases is all various forms of forecasting. What we're trying to get to is, how long will this feature take? Actually, we're not really trying to get to that. What we're trying to get to is when will this feature be done? We often ask how long will this take, but it's not what we mean, right? What we really want to know is when will it be done? How long it'll take almost doesn't matter. But we conflate these two things. And so what we're doing, again, is we're forecasting. But we're using an interesting form of math. And so really, I argue that we're forecasting sort of. It's actually a very poor form of forecasting. What are we doing? We take the current velocity or the average velocity of the past few iterations and we divide it into our best guess for the current work that needs to be done. And when we might graph it, we might just do the division, but regardless, let's say we graph it, right? So we have a top line that's the work to be done. We have the bottom line that shows our prior velocity, and then we have a little trend line, and where that trend line hits the top line, boom, that's the iteration within which all this work will be done. So the 8th iteration, now we can project what's the date. This is the typical format. Simple way of doing that is amount of work done, average velocity, divide the numbers, that gives you the number of iterations, right? You've all seen this. So my question to you is, are these forecasts accurate? I say they're not actually accurate. We might think that they're precise or whatever, but they're really not very accurate, right? But that's kind of a tough question to ask. A lot of people are like, yeah, they're pretty accurate. Okay, great. If they're accurate, then they should also be, are they definite? Well, no, they're not definite. Like, we're not definitely going to hit that. Maybe we will, we should. And then we get into this weird behavior around how, like, a thing that's not definite, if we don't hit it, it's somehow something about the ethics of the team or their character or their commitment, right? That seems pretty weird. But anyway, they're not definite. So better question is, are they probable? Well, yes, they're probable. There's a probability here. There's truly mathematically a probability. How probable are they? Not sure. How much confidence do you have when you forecast using this technique? Well, I think this is a good question. How probable is this forecasting technique? Right? Well, there's a way of looking at this mathematically, and there's actually a way of getting to probability that is much better than what we're doing. So how do we get to probable? Let's take a look at this. So what you need to know is pretty straightforward. You need to know your velocity, your backlog size, and the date that you're forecasting from. So I'm going to run a little mental exercise for you. The date today, by the way, is 10/27/21. So it's October 27th, 2021. The question is, can we get this done by January 26th, which happens to be 13 weeks from today? Can we get this done? So what do? We take 11, 10, 9, we average them. That's 10. We divide 130 by 10, we get 13. Our iterations are a week long. Hey, magic, 13 weeks. If we start today, we should be able to get this work done. Great. But how probable is that? Let's take a look at this tool that's available from the folks over at Focused Objective. Here's a link that'll get you to this tool. And I will provide some additional links at the end of the show. It's fairly straightforward. Here's a screenshot out of it. What I'm going to do is I'm going to actually head over to Excel and I'm going to show you this in more detail. All right, so here we are in the spreadsheet. We can see that today's date is 10/27/21. We have 130 units in the backlog and our average velocity is 10. Now, what this tool does is it takes your amount of work to be completed, and it takes your velocity range, which currently is 10, and it simulates a burn down. It chooses a number between in the middle of your velocity range, and it actually burns down, running iteration after iteration. It does that 500 times, and it charts your completion dates on a histogram and determines probability. Now, it's pretty sophisticated. It doesn't use a Gaussian curve. It actually uses a shifted Weibull. I'm not going to get into all of that detail, but trust me, this is a well thought out and proven technique. Now, what we notice with this is it then shows the likelihood over here. Now, because we've said it's 130 units and it's 10 units per iteration, and our iteration is 1 week, it shows us that we have somewhere between a 0 and 100% probability of finishing the work on 126. Interesting. That's pretty cool. But you remember that our velocity was actually based on a 9 and an 11. Now, when I punched those numbers in, it actually ran the 500 simulations and put them on a histogram and determined the probability. What happened? Well, what we notice is that suddenly 126 is at 55% probability, slightly better than a coin toss that we're actually going to hit that date. And it's more likely that we're going to come in on 2-2, right? Or it's a safer bet that we're going to come in on 2-2. Now, this is based on estimate. What this tool can also do is we can take more detailed. Here's our past 3 iterations, and here's prior iterations. It can take that history, and instead of doing an estimate, we can tell it to run based on our actual data and give us an even more realistic outlook. So we're now at 50% probability that we're going to hit the 126 date. It's a coin toss that we're going to hit that date. If we really want to have a high level of probability of hitting that date, if we want to be able to say, hey, you know what, we've got an 85 to 90% probability of completing this by 2/9, that's a much better conversation. If we want 100% probability, which is probably more than you need, then 3/2. What this is doing is giving us a much better insight. And the other thing that it's showing us is the standard math that we use is literally a 50% probability. If you think about it, that makes sense. We're taking the average and we're dividing our work remaining by the average, which would mean that, well, it's really no better than tossing it. So I recommend this tool highly. It gives you a much better conversation to have, very strong, very scientifically proven. Now, a challenge we have is, sooner or later, velocity is all over the place, and we're going to need to fix it, right? Let's take a look at this team. Now, we have here is a variable velocity graph. This is their velocity for the last 10 iterations, and you can see that it's up and down all over the place. So the question that I often ask folks is, looking at this graph, what can you tell me about the team? What is the challenge that they're facing? What is their primary challenge? Now, the answer, of course, is I don't know. But oftentimes what happens is people answer based on their own experience and bias. So they'll say, oh, there's too many dependencies, or the stories are too big, or they have a variable number of people on their team, or people went on vacation, or, right? So basically what ends up happening is we guess at what's wrong based on our own prior experience. We actually can't know from velocity what's wrong with this team. So if we were only focused on velocity, how on earth would we fix what's wrong with this team? And that's congruent with the advice of Deming. Deming says, look, setting quantitative goals doesn't matter. Fix the methods underlying those goals. Take a look at the data, see how it's trending. If it's not trending the way that you want it to, then look at the method by which those goals are attained. Get information about the innards of what's happening. So let's talk through a few things that might lead to variable velocity. First, and I think one of the most overlooked, is deferred maintenance. Now, many of you might call this technical debt. I have actually abandoned the term technical debt because it's so overloaded, it means nothing anymore. But fundamentally, this is no time to clean the code, no time to refactor, no time to upgrade infrastructure, right? We've deferred all of those basic maintenance functions till later, to the point that we've actually gummed up the system and we've caused it to move slower. So in the name of speed, we've actually slowed ourselves down. Now, how would we track this? One might be that you actually have deferred maintenance cards in your backlog. They might show up as refactoring cards or infrastructure cards or non-functional requirements. That's one way that you might, but another way, it's maybe a little bit closer to the team and a little bit more helpful, is we could take a look at code complexity. This is a simple metric that can be determined through static analysis. I won't get into the details of how complexity is measured, but it's really straightforward and it's easy enough to do and it's easy enough to learn how to resolve. But you want this measure because there is a positive correlation between code complexity and defects. The higher the complexity, the more likely there is that you've got bugs in the code. I can't tell you that a complexity of 27 means you're going to get one bug per iteration. It doesn't work that way, but what I can tell you is if your complexity is going up, so is your defect count. Speaking of defects, that's another thing that we can measure is escaped defects. Right? It's great to know, hey, how many defects did we get in this last iteration? Or how many were sourced in the iteration prior, etc. Escape defects are those that make it into production. So it's not development, not UAT. Those aren't escape defects. I don't consider those defects at all because they're part of our process pre-release, but I get that lots of folks do because release comes much later. Doesn't matter. We're talking about defects that are found in production. Go ahead and graph those. Now, this is a little bit misleading because the escaped defects really need to be looked at in relation to our throughput, or our velocity, if you will. So what we do is we take escape defects and throughput, and we actually average those together, and we get a graph that shows us the ratio of defects to throughput on an iteration by iteration basis. And we now have a sense of, is our overall quality increasing or decreasing relative to our rate of delivery? Great. All right. What else contributes to variable velocity? Well, a common one, and I've mentioned already, is batch size, right? Variable story size, consistently large stories. This is stories that don't get delivered until the feature is ready. It's a feature that doesn't get delivered until the release is ready. So there's a lot of batch sizes. There's stories, there's features, there's releases. All of these are different batches. And the bigger the batch, the worse off we are, right? The bigger the batch, the greater the risk. The greater the risk, the more planning required. The more planning required, the more time it takes. The more time it takes, the bigger the batch. This is a vicious cycle, right? The bigger the batch size, the greater the risk. One seemingly logical approach to this is to use story size as a proxy for batch size, and that can work, but I'd like to suggest some alternatives because story size for batch size leaves out releases and other factors. So what I tend to look at is release frequency. This is pretty straightforward. The reason this really works, assuming all other things are equal, so assuming the team size stays about the same, etc., the more often we release, the necessarily smaller the release must be. So if we're releasing every day, clearly we're not releasing as much stuff as when we released only once a month. So the more often we release, the necessarily smaller the release. So we can effectively use release frequency as a proxy for release size, and our release size is a batch size in this case. And small releases beat big releases every time. We get optionality, we get flexibility, we learn faster, and we get safety. Yes, we get safety from small releases more often. Small releases have a smaller surface area and a smaller impact. Each of those releases actually provides less risk and is easier to recover from. So what else can we look at in terms of batch sizes? Well, one of the things that we can look at that's fairly easy is coupling. So now coupling refers to the dependencies that are associated with a piece of code. And oftentimes a coupling graph or a dependency graph will show a node, which is code, and then it shows lines coming from that code that are the dependencies that code has. And sometimes you get a really tight and not so great looking coupling map. All right, that's a bit of a joke. They don't look like that, but they can look like this, where we've got a couple of modules and you can see all the lines between them and all the lines internal to them. Right. Now, this might be a shopping cart and a cash register, or an employee management and a payroll system. And they seem to know a lot about each other, right? Changes to the cash register would potentially break the shopping cart. Now, does that make sense to you? If a store got all new cash registers, would they also have to get all new shopping carts? It doesn't really make sense, right? Could the change to a payroll system break the employee? That doesn't make sense either. It shouldn't. And in addition, they seem to have a lot of connection paths internally. So there's some techniques that developers can use. One is to create a single set of interfaces between these two things and kind of hide their complexity. And then once you've done that, you can actually start to work on the internal complexity of each of those modules and start to break those down. And now you've got small pieces that are all independently releasable from one another, and you've significantly improved this. But coupling, the count of afferent and efferent coupling can be an indication of batch size, because things that are bound together, that are coupled together, have to move together unless we can reduce that coupling and make it soft. All right, what else leads to variable velocity? This also came up, work in progress, right? The more items in flight at any one time, the longer each individual item takes to get to completion. This creates the illusion of progress through busyness, but it actually impedes progress in terms of actual value delivered sooner. What you need to do is stop starting things and start finishing things. Don't start more work. Focus on finishing the work that you've already started. Let me take a look at this real quick. Here's a fairly clear example. Let's say you have 4 tasks of 8 hours each. It's a magic world. We know that they're 8 hours. Great. In theory, those would be done in a total of 32 hours, right? And so what we tend to do is we assign all 4 stories to someone and we say, hey, get these done. You've got 32 hours. But it doesn't work like this. When you work on something in parallel, let's say you work on each one for 2 hours and you kind of hope to switch, etc. Well, there's a tax for context switching. Plenty of studies have been done. This tax is about 20% for each new item, which means that it's fundamentally compounded. So in reality, these items would take 48.75 hours to complete. All four tests would not take 32 hours, but would take 48.75 hours. And for those of you paying attention, the first task, which is the blue, doesn't finish until past the 32-hour mark, where we originally thought all of them were going to be done. So nothing is completed until after we thought all of them were going to be completed. I know in reality it doesn't necessarily work out that way because priorities, because sometimes something is a little bit easier, any other number of reasons. Maybe the first one does get done right away. But on average, those tasks will take an extra amount of time, and in aggregate, they will take 48.75 hours. All right, so less work in progress. All right, I want to get one more thing in here for you. We'll talk about cumulative flow diagrams. Now, when I first started doing this talk, I would actually break down how you build a cumulative flow diagram. I don't do that anymore because plenty of tools do that for us, but I do want to show you kind of how to read one. So looking at this diagram, we can see a number of things. We can see work done and not done. We can see the amount of work in progress at any given time. We could see the lead time. So the time from, hey, wouldn't it be nice if, to the time when we say, hey, ain't that nice, right? Average lead time per item at any given moment in our history. And we can see the average cycle time for an item at any given moment in our history. And of course, we can see changes in scope. So there's quite a bit of information that's on this cumulative flow diagram. Those of you that are familiar with them, they should flow up and to the right. They should be relatively even flowed. They're relatively easy to read typically. So I'm going to go back to this team. Remember this chart? This is the team that had variable velocity. We talked about what might be contributing to this, and the truth is we don't know because we don't have enough information. Let's take a look at that same team with the same data, but now it's a different perspective. This is their cumulative flow diagram. I'm going to get you a second or two to look at this. Now, what you probably notice is that the green is quite large at times. What's happening is work is backing up and ready for approval. So for a number of months before I got to this client, they were having a real hard time with this team. This team just wasn't delivering. It was very unreliable. Their velocity was all over the place. Their delivery was all over the place. They just really couldn't figure out what was going on. And it turned out that when we looked at the broader system, when we stopped focusing in on the team, when we looked at the broader system, we discovered that, hey, it's not a team issue. It's not on the delivery team so much. It's broader, right? Their product owner is a traveling salesperson. And when they're on the road, they don't have time to review stories. Stories that aren't reviewed don't get approved. Stories that aren't approved don't go to production. They'd come back from off the road. They'd approve a ton of stories. They'd report a bunch of bugs. And then they would also add new stuff to the backlog because they learned things when they were out on the road that customers wanted. So we would very clearly see this pattern. It wasn't something that we could do with the developers or the QA folks. It was about their product owner and the way that all worked. All right, so I've got one last point that I want to share with you in this talk, and that is that metrics are not for managers, or more accurately, metrics are not just for managers. Metrics are for the teams. The intent of all of this data is to make it available to the team so that they can understand what's going on in their system and they can decide what adjustments they want to make. Thank you very much for watching the talk, and really appreciate you taking the time. If you send a blank email to onbelay@sendyourslides.com, make sure the subject line is escape velocity, all one word, no spaces. It will auto-respond with a ton of links, including all the resources and research behind this, and some information about my book, Escape Velocity. Again, thank you very much. Have a good day.